Drill pipe is the backbone of every oil and gas well, and JSH's production process shows just how much precision engineering goes into something that spends its life thousands of feet underground, under enormous torque and pressure. The process begins with carefully inspected seamless steel tubes selected for the appropriate grade, commonly S135 or X95 for modern directional drilling applications. The tube ends are machined to form an upset, a thickened section that provides extra wall thickness where stress concentrations are highest, right at the tool joint connection. This upset forging is done hot, using powerful hydraulic presses that compress and elongate the tube end under controlled temperature. Then the upset ends are rapidly quenched and tempered to achieve the required toughness and yield strength. Tool joints, the threaded male pin and female box connectors, are machined separately from alloy steel bar stock, with precision CNC lathes cutting the API or premium thread profiles that must make up reliably under field conditions. The threads are gauged to tight tolerances and phosphate-coated for corrosion protection. Joints are then friction welded to the pipe body, a process that generates heat through rotation and axial pressure, creating a metallurgically bonded joint without filler metal. After welding, the joint area is inspected by magnetic particle testing and ultrasonic methods to confirm weld integrity. The completed pipe is then full-body ultrasonically tested, hydrostatically pressure tested, and measured for straightness before receiving its final coating, typically a zinc-based internal lining for corrosion resistance and flow efficiency. There was a time when milling a precision metal part meant long hours of manual labor. A skilled machinist hunched over a manual mill, measuring, adjusting, cutting, and measuring again. It was an art form, no question about it. But today, the game has completely changed. What you're watching right now is the EMCO Concept Mill 260, a CNC milling machine that represents the very best of what modern manufacturing looks like in 2024. This isn't just a machine. It's a full machining center packed into an incredibly compact footprint. Let's talk power first. The Concept Mill 260 is equipped with a direct drive spindle, meaning there's no belt, no gearbox, just pure direct power from the motor, straight to the cutting tool. That spindle spins at up to 10,000 RPM with 6.8 kilowatts of power behind it. That's enough torque and speed to cut through aluminum, steel, and even hardened materials with remarkable precision. But speed alone means nothing without control. That's where the 24 meter per minute feed rate comes in, combined with a high feed force that keeps the tool cutting aggressively without chatter or vibration. The result? Parts that come out cleaner and faster than ever before. Now here's something that really sets this machine apart: the 20-position fixed tool magazine. Imagine having 20 different cutting tools loaded and ready at all times. No stopping, no manual tool changes. The machine's dual-arm automatic tool changer swaps tools in a blink, keeping production moving without interruption. And the brains of the operation? The EMCO WinNC control system, a CNC controller trusted in training facilities and production floors alike, paired with a beautiful 21.5-inch 16:9 industrial touchscreen and the intuitive, easy-to-control user interface. Even complex machining programs feel manageable. It's powerful enough for the pros, yet accessible enough for the next generation of machinists. If you've ever looked up at the skyline of a great European city, or admired the golden domes of a cathedral or palace, you've seen the end result of a metalworking craft that dates back centuries. Those beautiful curved, layered surfaces, they don't just appear out of nowhere. Each one is carefully shaped, panel by panel, with extraordinary precision. And today, we're going to watch exactly how that's done, using the Nyland hydraulic press. one of the most trusted tools in the decorative metalworking industry. The panels you're seeing formed here are called onion dome panels, named for their distinctive, bulging profile that tapers to a point at the top, very much like the shape of an onion. You'll find this architectural style across Russia, Eastern Europe, and the Middle East, adorning churches, mosques, and historic buildings. Each dome can require dozens, sometimes hundreds, of these individual panels, all formed to exact specifications so they fit together seamlessly. So how does the Neyland press turn a flat sheet of metal into one of these curved panels? It starts with sheet metal blanks, typically made from copper, zinc, or stainless steel, materials chosen for their durability, weather resistance, and beautiful appearance when finished. The press itself is a multi-stage forming machine. In the first stage, the flat blank is positioned carefully in the lower die. The upper die, shaped precisely to match the final panel profile, descends with enormous hydraulic force, pressing the metal into shape in a single powerful stroke. What's remarkable here is the level of detail in those dies. Every curve, every taper, every subtle contour is engineered into the tooling, so the panel emerges with perfect geometry every single time. But forming isn't done in one step. After the initial press stroke, the panel goes through edge trimming and flanging operations, where the edges are cut clean and folded slightly inward. These flanges are critical. They're what allows the panels to interlock and be fastened to the dome's substructure without any exposed fasteners or gaps. The Neyland press is especially prized for its repeatability. In a traditional hand-forming process, each panel would vary slightly depending on the craftsman. Here, every panel produced is virtually identical, which is essential when you're tiling hundreds of them across a dome that will be visible from miles away. Once formed, the panels are typically inspected against a master template, checked for any surface imperfections, and then either polished, coated, or patinated, depending on the final architectural specification. There's something deeply satisfying about watching this process. Ancient craft, modern machinery, working together to carry on a tradition that shaped some of the most iconic buildings in human history. That dome you admire on your travels? It started right here, on a press like this. Fire and metal. It's one of the oldest relationships in human history, and it's still at the very heart of modern manufacturing. What you're watching right now is the process of melting aluminum and copper. And while it might look straightforward, there's a whole world of precision science happening in that furnace. Let's start with aluminum. Aluminum melts at around 220 degrees Fahrenheit. That's about 660 degrees Celsius. It's actually one of the lower melting points of structural metals, which is part of why it's so popular in manufacturing. Lower melting temperature means less energy consumed, less wear on equipment, and faster production cycles. The furnaces you're seeing here are induction melting furnaces or gas-fired crucible furnaces, depending on the operation. Induction furnaces use powerful electromagnetic fields to generate heat directly inside the metal itself. No flame, just pure electrical energy converted into heat. It's clean, efficient, and incredibly fast. Once the aluminum reaches its molten state, you'll notice how it flows almost like water, smooth, bright, and intensely reflective. At this point, it's carefully skimmed to remove dross, the oxidized impurities that form on the surface. Skimming is critical because any contamination left in the melt will weaken the final casting. Now, copper is a different animal entirely. Copper melts at roughly 1984 degrees Fahrenheit, nearly 105 degrees Celsius. That's significantly hotter, and it requires more robust furnace equipment and greater operator care. But the payoff is worth it. Molten copper has an almost otherworldly orange-gold glow that's unlike anything else in manufacturing. Copper is alloyed to create brass and bronze, two of civilization's most historic metals. Even today, those alloys are critical in plumbing, electrical components, marine hardware, and decorative applications. After melting and alloying, the molten metal is poured into molds or dies, beginning its transformation from raw material into something functional and permanent. It's one of those manufacturing moments that never gets old, no matter how many times you've seen it. Every time you start your car, run your air conditioner, or flip on an industrial fan, there's a rotor at the heart of that electric motor, spinning thousands of times per minute, converting electrical energy into motion. And behind every rotor is a manufacturing process that has to be flawless. What you're seeing right now is the FVZ Automated Production Line, a fully integrated system specifically engineered for rotor manufacturing at scale. This is what modern factory automation looks like when it's done right. The FVZ line handles the complete rotor assembly sequence, from raw lamination stacks all the way to finished, balanced rotors ready for motor assembly. Let's walk through the key stages. It starts with lamination stacking thin silicon steel sheets, precisely punched and stacked to form the rotor core. The FVZ line automates this process with servo-driven stacking stations that align each lamination to within fractions of a millimeter. Even a slight misalignment here would cause vibration and imbalance in the finished motor. Next comes shaft pressing. The rotor core is pressed onto the motor shaft with carefully controlled hydraulic force. Too little force and the rotor slips. Too much and the laminations crack. The FVZ system monitors pressing force in real time, ensuring every rotor meets exact specifications. After pressing, rotors move to the copper bar insertion or die casting station, depending on the motor type. In die-cast rotors, molten aluminum is injected under high pressure into the rotor slots, forming the electrical conductors in a single operation. The line then feeds rotors into dynamic balancing machines, where high-speed sensors detect even the tiniest imbalance. Material is selectively removed or added until the rotor spins perfectly true. Finally, every rotor passes through electrical testing and dimensional inspection, ensuring continuity, resistance, and geometry all meet specification before it ever leaves the line. What makes the FVZ line extraordinary is its throughput without sacrificing precision. In a single shift, this line can produce hundreds of rotors, each one as precise as the last.